Okay, the final homework here is putting everything together. So I've got air conditioning systems providing cooling for a small office building in the summer. I've got cool dry air at state 2, just like the last problem, supplied to a conditioned state where it gets heated and humidified. This is done in such a way that the sensible and latent added together gives me the total QT for the space. There should be a n parenthesis there. Then air exits the space at state 3, goes into a return duct. Some of it gets recirculated, the rest gets exhausted from the building. The recirculated air is mixed with the fraction of incoming outdoor air, mostly to meet indoor air quality requirements. So we want to make sure that any contaminants, people are converting the oxygen to CO2. We want fresh oxygen coming into space. A number of other reasons. We want fresh outdoor air coming in. So we need to mix those two streams. The mixed air then is called state 1. When we put state 3 together with state 0, we'll get state 1. And then it's cooled to the dew point temperature, and then further cooled to a temperature that's at the, a humidity that's at the humidity ratio we want to send back into the space. So it's dehumidified to get it down to a lower temperature once it reaches the dew point temperature. Then finally the air is reheated with an electric heater. So that'll be at constant humidity ratio and then back to state 2 where we started. This makes a whole lot more sense on the psychrometric chart. So let me show this. So here's my space, and these are the conditions I want for my space. So it's 77 degrees and looks like about 50%. This is 10, 20, 30, 40, 52%, maybe something like that. Relative humidity. It's got a humidity ratio of a little greater than 0.01, so maybe 0.012. Then the outdoor air, it's about 95 degrees and looks like it's about 61% relative humidity, and that gets mixed with the return air. So this is the recirculated air, mixes with outdoor air, gives me state 1. And this fraction that I am along this line is called the percent outdoor air. So all the way here would be 100%, down here would be 0. So this looks like 60%, 55% on this sketch. I don't think these numbers on this sketch are exactly the same as the example problem. Then it gets cooled. This is called the dew point temperature for this state. So the dew point temperature for state 1 is the temperature where, if we cooled it at constant humidity ratio, where we would hit the saturation line, and that looks like around 36 degrees in this case. But then we continue to follow this line down here, the saturation curve. As it dehumidifies, it'll stay saturated that whole time until we get down to this humidity ratio that we want for state 2. So this is the exit of our cooling part of our air conditioning system. So it's saturated at the same humidity ratio as state 2. Then it gets heated in the electric heater until it gets to state 2 and then dumped back into the space. And the space does two things. It heats it and it humidifies it. And this state X here represents the enthalpy change for what's called sensible heating. And then this is called the latent heating, the constant temperature raising the humidity ratio. So again, this is our space, this is our supply air coming into the space, this process here, this is the electric heater for our air conditioning system, the cooling unit, which cools and dehumidifies, and then this is just mixing of two streams, outdoor air and our return air for the space. So now we just need to find all those states on the psychrometric chart, given what's specified. So let's start doing that. And go to the homework problem here. Let's see. There it is. All right, so state 3, let's start with that. It's 76 dry bulb and 63 wet bulb. So 76. And that slope looks okay there. 76 and 63 are red line is probably still okay. Slope of it, so that was 65, 64, 63. That slope isn't constant, but all those lines are pretty close. So looks like the slope of that's okay for this. And then we've got to move state 3 over here to this intersection. So I can move my label. So there's state 3. And ultimately I'll probably be wanting to know the enthalpy there. So let's just put that through that point. Looks like it's about 28.5. So assuming that's going to be asked for, 28.5. And the humidity ratio, we're looking for that state, so let's see if we can find that. I can move this line just temporarily through here. So right through that point, looks like there. And it looks like about 0.94, 0.0094. So 009, 0092, a little less than 0.0094, but that should be close enough. Okay, then we go on to state 2, and I want two things at state 2. The humidity ratio, actually a couple of things, humidity ratio, the temperature, and the specific enthalpy. So that's going to be a little hard to find since I don't have state 2 yet. So let's see what else we have to get us there. So I know that T1b is 49 degrees. So that's the exit of the cooling part of the air conditioning system. So let's look at the sketch here. So 49 degrees, if I bring this humidity ratio line down to 49 degrees, there's 50, and right there is 49. So this is 45, 46, 47, 48, 49. And if you can't figure out exactly which one this is labeling, you can always go to the bottom, and you'll see here, this is 50, and this is 49. So if I follow that line up, that would be 49 right there. And then I'm told one other thing about state 2. So I know that state 1b and state 2 are on the same humidity ratio line. So state 2 must be on this line somewhere. And then I need another line to define it. So if I go back, I find out that T3 minus T2 equals 21 degrees. So state 2 is 21 less than 76. So it looks like that would be 55. So 76 minus 21 is 55. So T2 is 55 degrees. And if I go to my chart, lay that down on 55, which looks like my slope's still okay there. So there's 55, so there's my state 2. And I can put the dot there if I want. Okay, and then I can move my enthalpy line there. Oops, wrong one. Put that one back if I need it. Okay, and that looks like about 21.3 maybe. There's 21, 21.2, I'm a little past that, so say 21.3. And that would be enthalpy of, so 21.3. And the temperature was 56, I believe. Let's take a look. 55. So it was 76 minus 21, 55 degrees. And the humidity ratio, we can look at that now. Looks like about 0.0074. Here's 007, 72, 74. So 0074. Okay, and then the enthalpy, specific enthalpy at state X. State X is at the same humidity ratio as state 2. So state X is this intersection of the temperature line for state 3 and the humidity ratio line for state 2. So let's copy this. Unfortunately, likes to move around. Okay, there's state X. And don't know why it likes to go to the top of the graph, but now the air doesn't have to go through that point. The air gets heated and humidified together, so there's a line connecting these 2 points. That's probably the real process, but it could heat it and then humidify it. So this from state 2 to state X is called the sensible heating, and this is called the latent. And that ratio of total, or sensible rather, this enthalpy change divided by the total enthalpy change, which would be from 2 to 3, is called the sensible heat factor. And I think that's asked for in this problem. So now I also want the enthalpy of that. And I would say that's 26.4. Okay, then the sensible heat factor. Is equal to Q sensible over Q total. And those are both multiplied by the same mass flow rate, so it would be the delta H sensible, which would be Hx minus H2 divided by H3 minus H2. And if I read those, so Hx I have is 26.4, 21.3. And I just need to find H3. H3 was 28.5. So I do the math there and get my sensible heat factor. So 5.1, and then that should have been the same number. I don't remember if it's 21.2 or 21.3. 21.3. So that was 5.1 divided by 7.2. So 5.1 divided by 7.2. So 70.8 or 0.708 is my sensible heat factor. Okay, and then the sensible heat transfer with the space, so that would be my mass flow rate times my delta H. So QS equals M times H x minus H2. And then Q total would be M times H3 minus H2. So that's the sensible. And apparently I need the mass flow rate first. So need to find that kind of given in reverse order. Let's see, actually that works okay. So the QT is given, so 55,000, so I can solve for, so we know what this equals, BTU per hour. So now I know H3 and H2, that's my 28.5, so I have that, I can solve for M then. So M equals QT divided by H3 minus H2, which is 55,000 H3 is 28.5 minus 21.3. And I will get forget that what that was, 7.2. So 55,000 divided by 7.2. So 7639. That would be pounds of air per hour. And the sensible, I haven't found that yet, but I could have. I know the sensible heat factor, which is sensible over total, so that would tell me that QS equals sensible heat factor times QT, so that is whatever my sensible heat factor was. It's 0.708 times 55,000. It's 38,940. That would be BTU per hour. That would be 8,940. Okay, so I'm cruising through my values. I can just double check that my Values are good. Correct, 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 correct. All right. The specific volume of the air at state 2. Should be able to get that from the chart. So this is 13.0, 13.1. This is 13.2, so I'll say 13.12, maybe 125. The volumetric flow rate of the air at state 2, that's just going to be the the volumetric flow divided by the specific volume is the mass flow, and I know the mass flow, so I can multiply it times the specific volume to get the volumetric flow rate. The specific volume of the air at state 0, that'll be the next thing, but let's go ahead and knock this out. The volumetric flow rate. So if we go back, let's take a look at our sketch again. I believe it's here. Okay, so we have air leaving this space and air coming into this space. We're assuming that that flow rate is the same, so we're not accumulating air in the space, and we don't have any extra flow of air in or out of the space. So the flow rate at 2 and 3 are the same, and that's the same flow rate at mass flow rate at 1B, 1A, and the supplier at 1. So the flow rate through this whole part of the loop is the same. When we get to here, some of this air left and some of this air mixes in, but that flow rate going around this loop is going to be the same mass flow rate all the time. So let's go back and see. So we were told the QT and the delta H, so we have the mass flow rate at, find that again here, the mass flow rate at state 2, and now we want the volumetric flow rate, state 2 still. Okay, so then we have that the mass flow rate equals EV over specific volume. So therefore EV equals mass flow rate times specific volume. And our mass flow rate was 7639 pounds per hour times the specific volume was 13.12 cubic feet per pound. So pound air cancels and I get cubic feet per hour, but I want cubic feet per minute, so times 1 hour divided by 60 minutes. So now we'll have cubic feet per minute. So 7639 times 13.12 divided by 60. So 1670 CFM. Okay, now we need to find state 0. So state 0 is 98 degrees and 60% relative humidity. temperature line, and let's get a new humidity ratio line. Okay, so this is our new one. 90 degrees. Looks like it's a little not steep enough, so trying to make it parallel. That might be close. That right on the edge there. And that looks pretty good. So 90 degrees and 60% looks like right there. So this is 60, 70, 80, 90, and 100%. So that's 60% relative humidity, 90 degrees. And that would be state 0. Guess I can label it. Actually, let me see if I can get both of them together. Okay, and I want a few things for that. I think I want the humidity ratio. So that looks like 0.0184. Humidity ratio. Okay, so I may be at the wrong place. So let's just check. It's 98 degrees and not 90 degrees. And it looks like a little steeper still. Like that. Trying to make those parallel, just so I know that I'm on the same line all the way up. Okay, so that's 98 degrees and 60%. Just make sure, so that'd be 70, 80, 90, 100. And somewhere they're labeled. There's 60%, that's the one that goes through there. Okay, then unfortunately, need to move my labels. Okay, now I can read it. So looks like 0.0238. Specific volume at state 0. It's almost all the way to this one. So this is 14.5, 14.6, so 14.59. Mass flow rate. Okay, so I've got volumetric flow rate was given 543, and I want the mass flow rate, so 543 divided by 14.59 is 37.22. And that's going to be per minute times 60, 2233. Right, at this point, I'm not going to write that down. I've written it down several times on the